In this video, we're going to walk through the solutions to a couple of practice problems. The first one is just trying to calculate standard free energy in a couple of different methods, using standard free energies of formation and then also using standard enthalpy and entropy values. So let's start with our first one. This one is asking us to calculate free energies or use standard free energies of formation to calculate the free energy of the reaction. And we have a reaction with methane and oxygen combusting to carbon dioxide and water. And I've pulled these from our lecture notes. We have our standard free energies of formation here. I've highlighted the ones that we need for our reaction, our carbon dioxide, our water in the gas state. And be careful of that because we have water in the gas state and we also have water here in the liquid state. And whether it's liquid or gas has an impact on what that value is. And then oxygen, which is an element, and so it's 0. The one that's not on here is methane that I had to look up in a data table. So it's here. It's negative 50.8 kilojoules per mole. So we're going to use these values and plug into our equation that we're going to develop. So thinking about our standard free energy equation, when we're using the formation standard free energies, we're going to say that our standard for the reaction is going to be equal to the sum of our product's standard free energy of formation times its coefficient. So that's going to look like this. And we're going to subtract from that the sum of the reactants, standard free energies of formation, multiplied by their coefficients in the reaction. Okay, so let's start moving numbers from our table over into our equation. We're going to see, let's start with carbon dioxide. So that's going to be negative, it's times 1. So we only have a coefficient of 1. It's negative 394.4 kilojoules per mole. I'm going to add to that my water, which is going to be 2 times that standard free energy of formation, because we have a coefficient right here of 2. I'm going to highlight that. So our water in the gas state is negative 228.57 kilojoules per mole. And that's going to be the sum for my product component. From that, I'm now going to subtract my reactants. So methane is a coefficient of 1, so it'll be 1 times my negative 50.8 kilojoules per mole. Plus then our water, or sorry, not our water, our oxygen has a coefficient of 2. So I would multiply 2 by the standard free entropy of formation, but since it's an element, it's 0. All right, plugging this all into a calculator is going to give me my standard free energy for the overall reaction, and I get a value equal to negative 800.74 kilojoules per mole. And just doing a quick kind of double check on this, we're talking about combustion. We're just burning methane. I know that that is an exothermic reaction, and it's taking particles in the liquid state and dispersing them out into the gas state. So it would mean that it would be increasing entropy. So I expect a negative value for my free energy change. And in fact, I see a negative value for my free energy change. It's a little like, whew, that at least makes sense. All right, let's try now the second method. So the second method for calculating a standard free energy is going to rely on our entropy and enthalpy values that we can pull from a table similar to the formation constants or the formation free energies we just did. So this one is referencing the problem that we did in earlier in our lectures, number 2, looking at ammonium and oxygen forming NO and H2O. So going back to that problem, we're going to treat this at 298 degrees Celsius. I was able to pull the information from a previous lecture, and I've got it here. So we can start with that. So the enthalpy, of the reaction, the standard enthalpy of reaction that was given was negative 905 kilojoules per mole. And we had used that to calculate the entropy. And when we did that calculation, we got a standard change in enthalpy that was equal to 3.04 kilojoules per mole Kelvin. So we're going to use these two values to calculate our free energy for the reaction, which will be equal to that enthalpy change minus the temperature times our change in entropy. So I can just basically plug in these values here. We're going to have our enthalpy value go right here. And let's do this. Entropy can go right here. And our temperature value, I'll make it, will come in right here. So plugging this in, we'll have negative 905 kilojoules per mole minus our temperature of 298 Kelvin times that entropy, which is positive, of 3.04 kilojoules per mole Kelvin. And looking at this, I have a positive entropy and a negative enthalpy. So this is an exothermic reaction that increases the amount of entropy in the system. And so I'm going from 9 moles of particles to 10 moles of particles in this reaction. And so it makes sense that I'm increasing that matter distribution over space. So I'm expecting a negative number. And when I plug this into my calculator, it doesn't disappoint. I get negative 1,810.92 kilojoules per mole.